That's cool. I'm going to go ahead and use my finger as a brake. I'm coming over here, and I'm going to go ahead and push the start button, and it's my job to stop it before it hits the ground. Again, like before, when we had to stop it, the first time we did this, when we had when we used the fan, we had to stop it before it crashed. Last time we were here, we did include it crashing into the spring. This time we want to stop it before the gravity stops pulling on the weight. Of course, gravity's always pulling on the weight, but the weight hanging down there, if you can see it, is going to crash into the floor. So I want to stop it before it crashes into the floor. So all I need to do is just click it once to start, and then click it again to collect it, to stop it before it hits. So I'm going to go ahead and play this game. I'm just going to go ahead and click it. I'm going to move my camera so you can see what's going on, and then I'll start and stop it. So here we go. Wonderful. And you can see it down there. It pulled it back up. It bounced. The whole system bounced. What caused the bounce was there's two magnets inside here. This thing is magnetic, so it's as if it was a spring. So there's a little bit of a tiny bounce. Let's go look at our data. Okay. So here's our data. Our data is off the screen over here. Here's our force sensor, and it measured all of these values while it was flying down. It looks like it's somewhere around 0.3, 0.35. Again, it was bouncing around a little bit. We mentioned there's a little bit of uncertainty, but the computer has gone ahead, taken all these values, I don't know how many there are, there's a bunch of them, maybe over 100, and it's averaged them and told us the mean. So we have that value. And over here, if I press this button, which shows me scale to fit, there's all of our data for our velocity, okay? Now, we're looking at velocity as a function of time, and again, we've played this game enough to realize that velocity as a function of time, if it's a constant acceleration, which is the constant of the force pulling on those masses, that we would expect this to be a perfectly straight line if this was a perfectly awesome world. You can see there's a little bit of a dippiness happening right there. That's fine. What we're going to do is we're going to fit this to a straight line, and we're going to ask the computer to sort of figure out what that is. There's a little bit of high there, a little bit of low there, high there. So there's a little bit of some wiggleness going through. The thick red line is what it actually is. What the problem is, again, it's not really a problem, but this version of this force sensor, they have a modern one that we haven't purchased yet. It's on our wish list. Is you'll notice that this thing has a cable next to it, or a tether, or an umbilical. And what happens is sometimes as this thing unfurls or uncoils, it causes this thing to slow down. So it causes it to slow down more than it should, and then it stops pulling on it, which makes it speed up maybe more than it should. So that's why it's a little bit more than not being perfectly straight. But we just fit the data. Again, it's a real-life lab. Maybe we can go to Bluetooth someday. It's a real-life lab, so real-life lab has real-life uncertainty. But we're just going to grab that slope. So I'm going to grab my pen over here. And run 1 with 0 Payload bars. What's the mass of the cart and the sensor? And again, we know what that guy is. So I'm going to write this down so we can look at it when we're at my desk. The cart and the sensor. The cart was 0.5 and the sensor was 0.339. The mass of the hanger and the masses was 35 grams, or 0.035 kilograms. I should go ahead and do that. 0.035 kilograms, 35 grams. The acceleration that was measured as the slope of the velocity, remember the slope, the rise over the run, the change in delta meters per second, the velocity versus the change in time, happens to be 0.269. 0.269. Okay, and oh, by the way, that is in meters per second divided by seconds. So meters per second squared. The acceleration calculated, that's what we're going to do when we sit down at the desk during our lab time, so I'll leave that empty for now. The force measured, meaning what did we actually measure? We measured a pull, which means it's negative, a pull of 0.31. So it was a negative 0.31 because it was a pull. It just meant that it was pulling it away. Force calculated, we're going to go ahead and do that later on when we sit down, but that's it. That was our first run. our next run is to repeat the experiment, but, oh, you know what? I made a mistake here. This needs to be 1 payload bar, and this needs to be 2 payload bars. Obviously, I changed the run 2 and the run 3, but I didn't update how many payload bars. This will be 1, this will be 2. I'll change that before I post this as a PDF. So what I want to do is take 1 payload bar, which looks like this guy, and put it in the center. That's ready to go. I have to come back here and I have to go ahead and delete my data. Experiment, delete last data run because I don't need it right now. That's cool. And we are good to go. So I just need to go ahead and pull this back up again. I think I will go ahead and press the tear button again. Here we go. That's all teared now. I can go ahead and pull this guy back. It sort of feels like I'm pulling back an arrow in a bow and arrow, because when I let go, it's going to fly forward. So there it is again. Doesn't have to be exact, just has to be somewhere. It's just hanging there. I haven't changed the amount of mass on the hanger, just the amount of mass payload-wise. I've added 0.5 kilogram. I'm going to go to start. Again, I'm going to let it go, press start to watch it moving, and then I'm going to press the stop button when that changes to stop before it hits. Here we go again. So here we go. Fantastic. All right, here we go. You'll notice I haven't changed this. The data is a lot lower than it was before because the velocity is a little lower. I'm going to press the show me all the information. And this time around, my slope was 0.17. So my slope down here. So again, mass of cart and sensor was 0.5 plus 0.339 plus 0.5 because it had a payload. Mass of hanger and masses is still 0.035 kilograms. That hasn't changed. The acceleration, we had 0.269 before, and now I only have 0.17. 0.170, and that's meters per second squared. So we're going to find out if that's a good value or not, but you can see that it's slowed down. The fact that if you will, the little tiny masses on the end of that string were pulling this payload like pulling a sled, and then we made it heavier. So it was still pulling the same amount, but that means that it didn't accelerate as fast. Okay. So let's do it a third time, and then we'll get out of here. I go ahead and take my other payload. I'm going to take off this guy and press the tear button again a couple times. Move this guy back. Again, it feels like I'm pulling back an arrow inside a bow. There we go, or a crossbow bolt in a crossbow. Pick your analogy. I have to go ahead and before I do anything, I have to go to experiment. And I have to delete the last data run and say, okay. Okay, here we go. Oh, crap. I didn't write down the force measured mean because I'm an idiot. Darn it. Here we go again. Let's run some data again. This is what I talk about all the time as far as if you have a goof, make sure you don't ungoof it. Let's run it again. Here we go. So let's do number 2. Let's give it a shot. Okay, here we go. What time did I get this time? I got a little bit different acceleration this time. Of course I did. So I'm not sure why it's different. It just is. Everything seems to be good. So I need to cross this out because it was a goof and put in 0.166. 0.166. So last time it was 17 and this time it was 16.6. That's fine. Meters per second squared. And before I run away, because I'm an idiot, I need to calculate this guy. Negative 0.31. Negative 0.31. Well, look at that. I didn't mind running it again, but notice that the pull the first time is the same as the pull the second time because we didn't change the amount of masses on the little mass hanger. It was, what was it? it was 0.31 the first time. Of course it was 0.31 the second time. Maybe I should have known that, but of course I wanted to verify that. So with 0.31 the second time we did it, we got a slope of 0.166. But again, that's what you do when we do data. So I'm going to go ahead and delete this last data run. Say, okay, let's try this again. We're not changing the data on the end of the string. We're adding a second payload. For now, it's a total mass of 1 kilogram extra. I'm going to pull. Oh, I didn't. Again, got to do everything right. I teared my my payload. Go ahead and pull this guy back again. You can do it. There we go. It's ready to go. Okay, I think I'm all set. Start it is. Here we go. Let's start it and run it and see what happens. Lovely. And again, you can see it sort of bouncing down there. It's bounced back up again. I don't know if you also noticed it sort of moved my rail a little bit the second time and a lot of it the third time. We're going to be talking about crashes in a little bit, and that's momentum. There's a lot more mass that needed to be stopped this third time around, which caused this thing to jerk really, really hard. It's all physics. I love it. 3 payload bars, massive cart and sensor. 0.5 for the cart plus 0.339 for the sensor, plus this time around 1.0 kilograms for the payload. Massive hangar and masses 0.035 kilograms. That hasn't changed. Acceleration measured. I need the slope. This time around, the slope is even lower. It's still sitting there on the screen, but if I press this button here, I can see all the data. In fact, this is really, really smooth. That looks like great data. It's 0.102. 0.102 meters per second squared. And the force measured is, okay, I'm waiting for, oh crap, look at that. 0.31, negative 0.31. Again, these are all newtons, and these are newtons, and these are newtons. I'm not sure why I said this, but this is a pool. Fantastic. So our pool, our force, didn't change for all 3 runs because we didn't mess with the amount of mass on the end of the string. But what did change was the measured acceleration of this little guy back here in its lightest, in its least mass configuration, just 0.5 plus 0.339, it accelerated the fastest, 0.269. The second time around, when we added mass, it didn't accelerate as fast. It only accelerated at 0.166. And when we added even more mass, it didn't accelerate even more, even at 0.166. It's way down here at 0.102. So if you're designing a muscle car to be at the starting line and you get the starting change of beep, 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 go, if you're not going to change the engine and you're not going to change the amount of horsepower or force that propels it forward, then you have to make the car lighter. If you make the car heavier or more massive, the same amount of push or pull is going to reduce the acceleration and make the car slower. All these things that we've studied before. If you've heard about mass and force, we're going to do that. And we have some questions back here. So we're going to look at these questions when we get together again on Monday. But for now, this is the data that we needed in order to take a look at this guy. Fantastic. So we're over here. I'm going to go ahead and push this off, and I will see you in the future. Thanks.